Okay, thank you. So, okay. So, hi, I'm Subrata Samanta. I'm first year PhD student at IIT Kanpur. So, I am your teaching assistant for the thermodynamics course taken by Professor Nirmala Banerjee this semester at NPTEL. So, today I will briefly discuss the radiations, mainly the cavity radiations, and some related thermodynamics. And next, I will solve some problems that might help to solve assignment problems. It will be helpful for those students who appear for the exams, and I will also continue to this to the next sessions. I mean the 21st April. So I request you to please be there and clear your doubts before your exams. And I will suggest you to do the calculations along with me so that you can check the answer and better understand the problems. So let me bring out my screen first. Okay, so I hope my screen is visible now. Okay, so my screen is visible, right? So today we discuss first. Today we first discuss the yeah. So my screen is visible, right? Okay, so my screen is visible, right? Okay. So let's consider. So we'll start discussing briefly about the radiations, and then we will solve the problem. And next sessions we also solve the problems that help the students are appearing in the exams. So let's consider a container. So first consider a let's consider a container of volume V and temperature T. Container held at temperature T. Temperature T. And this surrounding by this container, it looks like a cavity. So surrounding of this container, it looks like a cavity. Looks like a cavity. So that basically means that suppose we have a container of, let's say, volume V at held at temperature T, and the surrounding of this. So this container kept in the surrounding. This looks like a cavity. Okay, in that surroundings. So this container looks like a cavity in that surroundings. So, and this now the this container temperature is like it's a cavity temperature. Okay, and inside the cavity there is some radiations. Let's say write this volume V and So now inside the cavity there is some radiations. So this is the thermal radiations. So what is this? That suppose the electromagnetic life classically looks like a wave, electromagnetic radiations. But if any object that any object content at non-zero temperatures, okay, so they emit radiations. This is called the thermal radiations. So the electromagnetic radiations emitted from the object which is held at non-zero temperatures, okay, it's called the thermal radiations. Okay. And this object, this cavity content held at temperature T, okay, and they emit radiations. This is called the thermal radiations. Okay, and the radiations inside the cavity. So the radiation inside the cavity, okay, are in thermal equilibrium with the cavity wall. So this the circle is the cavity wall. The circle is the cavity wall, and the radiation inside the cavity are in thermal equilibrium. Are in thermal equilibrium with the cavity wall. With the cavity wall, because both are at same temperatures. So the system, so we consider cavity later we consider cavity as a thermodynamical systems, and the surroundings both are held at constant temperature T. That means they are thermal equilibrium, and the radiations are also in thermal equilibrium. That means they form a standing waves. So they form a standing waves. So this radiation is a kind of waves, and due to this thermal equilibrium, so they form a standing waves. And this wall, so so while we consider that the wall is a diathermal wall, so when we consider the wall is a diathermal wall, that means they transmit heat between the uh, gas of photon inside the cavity and the surroundings. So we consider the here we consider the cavity wall is a diathermal wall. Consider the cavity wall. Cavity wall. Yeah. Cavity walls are diathermal. Diathermal. So that means so they transmit heat between the gas. They transmit heat between the gas of photon, gas of photon inside the cavity and the surrounding. Inside the cavity and the surrounding. So that means the diathermal walls means that the heat transmit is possible through this wall. And that's why they are in thermal equilibrium, and the standing waves produce. So what is this gas of photon? The gas of photon is that, so according to Planck, so these radiations, the electromagnetic radiations or for thermal objects is a thermal radiations, right? So can be quantized and as a set of photons. So according to Planck, according to Planck, this radiation, with this radiation waves can be quantized as a set of particles, as a set of particles. So these particles called the photons. These particles called the photons, right? And so then there, if suppose consider the n photon in the unit volume of this container, comprise the gas of. So n photon, uh, so so they call photons. Now the n photon in per unit volume inside the cavity, n photon, if n photon, so if n photon per unit volume, per unit volume inside the cavity, comprise the gas of photons. Comprise the gas of photon. N. So n photon per unit volume comprise the gas of photon. And we study this thermodynamics of this photon gas. Okay, so then okay, so that this photon, so quantum mechanically the photon is energy. So each photon quantum mechanically this each photon have energy. Each photon have energy each photon has energy equals to h times nu. Nu is the frequency of these radiations. So nu is the frequency of this radiation, and h is the Planck constant. Planck's constant. So h is the Planck constant, and each photon has energy h nu. So then there is a n photons in per unit volume. So the energy density, so energy density of the gas U, this is the energy density U, this is n times energy of each photon. There is a n photon and energy of each photon EP. So that means n h nu. This is the energy density, right? And so you can write this energy density as a U by V. total energy per total volume. Right? So this is a total energy per unit total energy. So now from kinetic theory, so we know that so we will discuss that how far can we go just thermodynamic arguments. So we will mainly discuss that how far can we go, how far can we go just macroscopic argument. How far can we go just thermodynamic arguments. So we consider a cavity as a thermodynamical system and how far we can go or predict about the systems or about this radiations, photon gas. So how far can just go for just thermodynamic arguments? That means the macroscopic arguments. And we will explicitly see that the where this macroscopic argument fails and we need a microscopic picture, that means the quantum mechanical picture. So macroscopic means that the classical pictures. So where this macroscopic and thermodynamic argument fails to predict, okay, and what kind of problems are appears, and that's why we need a quantum mechanical argument that compensate these problems. Okay, so so how far can I go this? So in the first class or second class, we study these kind of things that suppose there is a cavity. This cavity looks like a container, okay, and there is a detector. There is a let's say, so there is a let's say detector. So this is a let's say cavity. So this cavity filled with a photon gas or thermal radiations, and this is a detector, and this is a area A. This is a spherical cavity, and we consider a small part of this surface area. This is area A, and this is like a detector. So you can think of this that we study in the first few classes, that if there is a wall, okay, and we consider a small part of this wall, that's area is A, and the gas heating to this particular area, let's say at angle theta to this normal. So the gas molecules, so from kinetic theory, when we study the kinetic theory of gases, okay, so we will discuss this thing, that the gas molecules heat to the surface of this, so this is surface. So this is the surface, and consider a small part of this surface with the area A, and gas molecule heat to the surface area at an angle theta to this normal of the surface. So at delta time the speed is, if the speed is c, so c delta t. At delta time there is the distance c delta t. Let's see this. So now we calculate the flux, okay, energy flux. Calculate the energy flux. Energy flux. So first we calculate the pressure. So the energy flux phi per unit frequency in case of this radiation. That's why I call the frequency. So the energy flux per unit frequency, this phi is 14 cu. U is the energy density, and we end up with the pressure P. So the pressure from this binding theory basis, we know that this derived as 1/3 m and the v square is value. Here is the velocity c, so c square. Right? So 1/3 m c square, and the flux is the phi is 1/4 c times u. So the similar situations, this cavity and so the similar situations here and here. So it looks like a proton gas inside the cavity. So and just so this comes from this kinetic theory of gases. Okay. So while considered a perfect gas, okay, and they hit to the walls, and we calculate the pressure. This 1/3 m c square. So now we apply from this for the proton gas. Okay. So for proton gas, it's not an ideal gas. So proton gas is not a perfect gas. So for proton gas, say that this mc square is a energy. So energy is a mc square. Interpreting this mc square as the energy of the photon. Classical. So quantum, this is this energy of the photon H nu is a quantum mechanical. But here we deal with the kinetic theory of gases. Okay. So we have adopt this formula from the kinetic theory of gases. Okay. So that's why we write that each photon has energy E equals to mc square, and then the pressure P is 1/3 n times E, right? From this. So now this n times E, it's nothing but this is the energy density U, right? N times EP. My screen is visible. Yes. So now we see that the energy density U equals to n times EP, right? So this is the number of photon times energy of each photon. So this is just exact this. So each photon EP, let's say this P. So this is just P actually U by 3. So for photon gas, the pressure is 1/3 of the energy density. Okay. So this P is a pressure. Pressure is 1 by U by 3. But for ideal gas, for perfect gas, so for perfect gas, this is not the case. For perfect gas, this E energy is for perfect gas. For ideal gas, what is the energy? It's half m v square, right? Half m let's say c square. So here is the velocity is c. Right? So for photon gas, the c is nothing but the speed of light, because this is a relativistic gas. So this c is a speed of light. C equals to speed of light. But in this case, the C is a speed of gas. Okay, because we are considering the gas molecule for kinetic theory part. For ideal gas, you just adopt the same idea here, but consider different gas. The relativistic gas, okay, so they move the speed of light c. So the velocity we just replace with the speed of light c. So there are two different meanings. Let's say here we denoted as the v square. Without any confusion, this is a v square, the velocity. of the gas molecule, and here is the this V will replaced by C. So V tends to C for photon gas. So now for ideal gas, for perfect gas means that the ideal gas, so energy is half mv square, right? For only one direction. So then this P is 2 by 30. If there is a in molecule, so total energy density you is 2 by 30. It's not a 1 by 30. So for perfect gas, perfect gas means that the ideal. So these two different things. So how the pressure and energy density relate for ideal gas and for photon gas. So in general, so this actually comes from the dispersion relation. So okay, so look, what the difference is? So the difference is that the energy, right? So if the energy is mc square, then there is a 1 by 3. If the energy is half mv square, then there is a 2 by 3. But how this energy comes? This comes from the equipoisson theorem, right? So if your uh, dispersion relations, energy is proportional to, let's say, k to the power n. This k is a momentum, or p to the power n. So p is a momentum. So then, from the equipoisson theorem, we know. So this is, let's say, Hamiltonian H. So H is proportional to p to the power n. So this p is a momentum, and then from equipoisson theorem, we know that the energy E is 1 over n. That's a kb. So we just focusing on this 1 over n factor. It's focusing here 1 over n factor. So for ideal gas, this H is nothing but the p square over 2m. Okay, only kinetic energy, right? This is the Hamiltonian. P square over 2m, only kinetic energy. There is no potential energy. From this, we get that half kb. Right? This is exactly that half mv square. Okay. But for photon gas, this is for the ideal gas. And we end up with that P actually 2 by 30. Right? Now for photon gas, for relativistic gas, this equation is not valid. A is equals to p square by 2m is not valid. So for photon gas, the equation is that I am write this energy E equals to P. So they depend on the p to the power 1, and this energy is just a Hamiltonian. So from this case, getting that E equals to P equals to, let's say, mc, so mc square. Then you know that the P equals to mc for relativistic. So that's why we get a E equals to mc square. So the Hamiltonian energy are the same footing. So this E is proportional to P, right? That's why this P is 130, right? So that means if p to the power n, then we can calculate accordingly the P. Okay, what is the P? Okay. So you can generalize this thing in this way. Okay, so what is the flux? So the flux is that 1 by 4 Cu. And this is true, because we know that the energy density, and this is c. For gas, this is the velocity of the gas, and for proton gas, this is the velocity of light. So the flux is the same formula. The flux, yeah. So this flux per unit area. So flux per unit area is 1/4 u c. So consider the only photon gas. So 1/4 CV, where c is the speed of light for photon gas, the c is the speed of light, and u is the energy density. Okay. So this flux of the photons in this container, so there is a radiation, and this the flux of this photon in this container on the walls of the container, and that equal that the same putting that the number of photon gas taking to this unit area, okay, unit time. This is the flux. So flux per unit area. So flux is means that the definitions that the number of photons streaking per unit area per unit time, number of photons streaking to the wall per unit area or unit time. This is the right way to say it. And this is the flux. The number of photons taking per unit area per unit time to the wall is the flux. And this flux is 1/4 c. So now we do some thermodynamics. And this relation is important. So from this flux, sorry, 1/4 c. Yeah. So here this is not u, this is n. It's the number density. Sorry, n photon number density. It's the n photons, and for this case, this is also nc. Okay. Let's look into this. I have a note, so yeah. So here we derive this kind of things, right? So this pressure is 1/3 mc square, and then we derive the flux. Yeah. Flux is n, right? So n times V average. So 1/4 n times V average. So where n is, it's a number. Okay? So P equals to n kmt. For the number density per unit volume, we take the number, right? So n photon per unit volume, that means the number density. So okay. Yeah, so this is n, and this V average here is the c. Right? V average square, the right way to say, and this V average here is the c, the velocity of light. This n is the n photon per unit volume. That means this is a number density. So now, so this is a flux. So now we write on the power incident. So the power incident per unit area of the cavity. So what is the power incident per unit area of the capital. So this is the power P. So this is not a pressure. Okay? This is a power. Capital P is power. So this power is just so we multiply with the energy of the photon EP times 1 by 4 MC. Now this gives that N times EP is equal to energy density and density. So power is 1 by 4 C. And this relation is important. So these relations derive the Stefan Boltzmann law that relates the temperature of a body to the energy flux radiating from it. So if we know the temperature of a body, okay, and if we know that how much flux radiating from this body, they relate this. So these relations helps to derive the Stefan Boltzmann law. So we will see this. So let's first discuss some thermodynamics. So recall our first law of thermodynamics, that the first law of thermodynamics tells you that du, change in total internal energy du, is TdS minus PdV. This is a small speed pressure and dV. So now we derivative this with respect to the volume at constant temperature. So that del U del V at constant temperature T, T del S del V at constant temperature minus P pressure. So now we use the Maxwell relations. So the Maxwell relations tells that del S del V at constant temperature is equals to del P del T at constant volume. So if we put this, we get at the T del P del T, this is a small pressure, del P del T at constant volume minus P. Right? So now we know that the pressure P for photon gas is 1/3 U. Right? Just put it here that the T 1/3 del U del T at constant volume minus pressure. Okay, P is equal to Y. And this del U del V, this del U del V at constant temperature is nothing but the energy density. How do we know? We know that this U, the energy density is U by V. So now if U is small u times capital V, del U del V at constant temperature, we derivative this, we get this U plus V times del U del V at capital at constant T. So now the del U del V is that 0 because the energy density, that means that U by V, that is the energy, total energy per unit volume. So that is independent of the volume. Right? So this U is the independent of the volume. U is the independent of volume. So energy density does not depend on the volume because this is a total energy per unit volume. So the same for any unit volume. Consider any unit volume. So this is the same. So this is the independent of the total volume. So independent of the volume. So that's why this U equals to this del U del P T. So then so this implies that this 4U equals to T times delta U over delta T at constant volume V. So now we replace this partial because there is only variable is T. So we replace this partial derivative to the total derivatives. So 4 dt by T equals to U by T. Okay. So remember that U is only functions of T and the derivative here is the del U by del T. So that's why we replace this partial derivative the total derivative. But this is not the case always. Suppose u is depends on both v and t, then we cannot do this thing. So this implies that u is a times t to the power 4. Just integrating once and we get this. So a is an integration constant. So u is a times t to the power 4. So the energy density, so here a is a constant. So the energy density is proportional to t to the power 4. So now by dimension analysis we can write down the dimensions of this a, the constant a. This constant a dimension is that joule, or the unit is joule, Kelvin inverse, and meter to the power minus 3. So similarly, if we calculate the pressure, or the power, so if we calculate the power incident on the wall, power incident per unit area on the wall, power incident per unit area of the wall, is the capital P. So what is the formula? Power incident per unit area of the wall. So it's just a 1 by 4 c, we derive this. So 1 by 4 c times, what is the u? A times t to the power 4. So that is the sigma times t to the power 4. Okay. So the sigma is 1 by 4 a times c. This is called the Stefan Boltzmann constant. Sigma is called the Stefan Boltzmann constant. Boltzmann constant, and this is the Stefan law. Stefan's law, Stefan Boltzmann. So the third is called that the Stefan's law. So what this Stefan's law tells? We just say before that. So how the energy flux radiating from a body is related to the temperatures. So this is a power, that means the power incident. So this is related to the temperatures. So U is A to the power 4, or the pressure power is sigma to the power 4. So both are the equivalent form of the Stefan's law. So that means that the flux, actually the flux is proportional to the power 4. The flux incident on the cavity wall is proportional to the T to the power 4, the temperature of the cavity. So they relates Stefan's law the temperature of a body. So relates the temperature of a body to the energy flux radiating from it. Okay. Energy flux radiating from it. So if we derive this E is equals to sigma times T to the power 4, we need this. We need this formula. That's why I tell you what is the importance of this. But how to calculate this sigma, this constant? So from macroscopic viewpoint, there is a no way to calculate this. So if we calculate the sigma from experiments, or from theoretical viewpoint, you can also calculate from the statistical mechanics. That's why we need the microscopic descriptions, the quantum mechanical descriptions, in order to calculate this sigma constant. Otherwise, you can extract from the experiment. So initially, this sigma determined from experiment, but later from statistical mechanics, when develop the statistical mechanics, that means the microscopic picture, and then we can also determine this constant and the match with experiment. So that is the ongoing progress in this area. So now we define one more term is called the spectral energy density. So the energy density of this radiations of this gas, okay, is a quantity that which tells you how many joules of are stored in cubic meter cube of cavity. Right? So per unit volume, okay, how much total energy are stored. Okay, that is the tells you that this the energy density. So far we discussed. But what we want to do now is to specify that which frequency range that energy is stored. So now we want to do now we want to specify in which frequency range this energy is stored. Which frequency range that energy is stored. Energy which stored. So energy density is not a good observable to tell. Okay? So we have to specify that in a specific range of the frequency or wavelength, and that is that the spectral energy density. So define spectral energy density. Spectral energy density. So this is, let's say, u lambda, some range lambda to lambda plus d lambda. So it's defined as follows that this u lambda d lambda, u lambda times d lambda, because we are in tested in this region, that lambda to lambda plus d lambda. So in this range, the u lambda is the energy density. This is not an energy density; it's called the spectral energy density or spectral density. Depend on some spectrum. Which region of the spectrum you are interested. So this u lambda d lambda. So u lambda d lambda is the energy density. Is the energy density. Is the energy density due to those photons which have wavelength lambda and lambda and lambda plus d lambda. So this is not an energy density of each photon. So those photon whose wavelength lies in this range, lambda and lambda plus t lambda, and their energy density is called the u lambda. Okay, and this is called the spectral energy density. So the total energy density total energy density u. How to write? Integrate u lambda and d lambda. So integrate over all range of lambda, and that gives a total energy density. So just to split the total energy density as a part of the different range, and that is called the spectral energy density. So just to integrate this u lambda d lambda over the all range of this lambda, it gives a total energy density. And similar way we can also define this u nu. So u nu, that is that the range is nu and nu plus d. Nu plus d nu frequency. So same definition. Same way we can define that the u nu is the nu and nu plus d nu frequency. So here we written in terms of the wavelength. Here we written in terms of the wavelength, but we can define also this u nu in terms of the frequency. Similar. Yeah. So now the second is that in thermal equilibrium, there is no net energy flux from cavity to the surrounding. Right? So that means that the energy flux from one cavity to other is the same. What do you mean? That means that the power actually, so in thermal equilibrium, so in thermal equilibrium, that the power emission and the power absorption is equal. So the power emissions on the wall, power emissions from the wall of the cavity and power absorptions on the walls are equal. So power emission and power absorptions are equal. So let's consider two containers. So one container, let's consider two containers. And they connected a tube, and there is another container. So let's say this container A and this is container B. So they connect with a reservoir at temperature T. This container also connect with a reservoir at temperature T. Right? And they connected through a tube. Both two containers connected through a tube. Now, if these two reservoirs at same temperature, so they in thermal equilibrium. So from the second law of thermodynamics, that the no heat flow from one container to another, because they are in thermal equilibrium and both are same temperatures. So the no heat flow from one container to another. So therefore, no net energy flux from one container from another. Okay. So no from second law of thermodynamics. From second law of thermodynamics, no energy flux so no net energy flux, no net energy flux, energy flux along the tube, along the tube. So this is a tube. So no net energy flux along the tube. So that means that the energy flux from a container emitted from the A container, and this must be absorbed in the B container. They must balance, because I have seen that the no net energy flux along the tube. So the energy flux must be balanced. So that means the energy flux must be balanced along the tube. Energy flux must be balanced along the tube. So what does this imply? So this implies that, so what is the flux? This flux is 1 by 4 NC, and this pressure is power is 1 by 4 UC. So this energy flux phi, so that implies that the power must be equal. So power emission and power absorptions are equal. So that means that U A and U B are equal. Okay. So the energy density U must be the same. So irrespective of the size, suppose cavity A is bigger than the cavity B, still the energy density is same for the both cavity. So that means that the energy density must be the same irrespective of the size. So both the cavity, so that means that both the cavity must have same energy density, must have same energy density irrespective of their shape. So they can this containers can make any shape, size, okay, and material of the cap. So I call the cavity or container. So same energy density irrespective of their size, shape, and material. A similar way, we can also tells that the spectral energy density also same. Because suppose you consider a tube that only pass the wavelength lambda to lambda plus d. Right. So we consider a tube that too narrow that only pass the wavelength lambda to lambda plus d. So then this u lambda A cavity at temperature T and u lambda B cavity at temperature T is also same. So spectral energy density also same. So spectral energy density is also follow the same thing that they independent of the shape, size, and the nature of the chemical material of the chemical. So spectral energy density follow the same thing. Spectral energy density follow the same thing. Actually, as you specifically written that the spectral energy density has no dependence. No dependence of on the material, shape, size, and nature of the chemical. No dependence. Yeah. So far, any questions? Yeah. So from this, we can state the Kirchhoff law. So, how well a particular surface of a cavity will absorb or emit electromagnetic radiations in a particular frequency. So, so that tells that the Kirchhoff law. So, so then we define two additional quantities that the spectral absorptivity, absorb- that is called the alpha lambda. So I am defined for the lambda. So in the same way for the frequency case also alpha nu same definition. So here I am only considering for the lambda to lambda plus t. In the same way you can consider from mu to mu plus t for the frequency case. Yeah. So far any questions or any point if you are not understood clearly, then I can repeat this. Okay. So the spectral absorptivity is the fraction of incident radiations which is absorbed at wavelength level. Okay. So it's the fraction of incident absorbed at wavelength lambda. Absorbed at wavelength lambda. And similarly, the other things that spectral emissive power. So spectral emissive power, that is called the E lambda. Let's say we define this thing, these two things. So spectral emissive power. So of a surface, a function such that the E lambda D lambda is the power. So the spectral emissive power of a surface is a function such that the E lambda D lambda is E lambda times this frequency, wavelength range, so lambda to lambda plus D lambda. So E lambda D lambda is the power emitted per unit area by this thermal radiation having wavelength lambda to lambda plus d lambda. So spectral absorptivity is the fraction of incident radiation which is absorbed at a wavelength lambda, and emissive power is that the power emitted per unit area by this thermal radiations having this wavelength lambda to lambda plus d lambda. Right. So then the Kirchhoff law tells that this E lambda alpha lambda, so we the E lambda divided by alpha lambda it's nothing but that the 3 by 4 U lambda. So remember, this is in equilibrium. So in thermal equilibrium. So this incident power. So we define. So this is a power emitted. So emissive power and power absorptions are equal, right? So power absorptions in thermal equilibrium, then the power P absorptions equals to power emission. So these two powers are equal. So then we can write the power absorptions in terms of this U lambda and D lambda times. You know this thing. That power absorptions is that so it implies that just write this thing that what is the power absorption? It's 1 by 4 U lambda times D lambda, lambda to lambda plus D lambda, this is energy density. Then times multiplied with C times the alpha lambda. So alpha lambda your absorptivity, the fractions of incident radiation which is absorbed. So that's why multiplied with the alpha lambda. This is equals to the emissive power U lambda D lambda. Then we end up with this. This is called the Kirchhoff law. So that means that this E lambda by alpha lambda is a universal functions of lambda and D. It is independent of the volume. So if we fix the lambda and t, so that means this is a Kirchhoff law. Kirchhoff law. So this tells that this E lambda or alpha lambda is a universal function. Is a universal functions of lambda, and u lambda is a functions of t, right? Is proportional to the power 4. So lambda and t, universal functions of lambda and t. So if we fix lambda and t, if we fix lambda and t, let's say a particular range lambda to lambda plus t lambda, we fix the lambda and the temperatures of the cavity, then this E lambda is proportional to alpha lambda. So that means that good absorber is a good emitter and bad absorber is a bad emitter. With alpha lambda and E lambda proportional. If a good absorber, that means the alpha lambda is high, so that means it automatically tells that the E lambda is also negative, and similar for the others. And for perfect black body, where this alpha lambda equals to 1 for all lambda. Okay, so for the black body, a perfect black body is an object. A perfect black body is an object which is defined to be that where the alpha lambda equals to 1 for all values of lambda. So in which alpha lambda equals to lambda for all values of lambda, and that is called the perfect black body. And the radiations from this black body is called the black body radiations. So these kind of objects, the radiations from this kind of object is called the black body radiations. So the radiations for or the gas of photon content in the black body, in this black body cavity, content gas of photon content in this black body cavity so black body cavity is that the cavity which walls are this perfectly absorbable where the alpha lambda equals to 1. So that is called the black body cavity, and the gas of photon inside the black body cavity, because there is some radiations, and this gas of photons content in this black body radiations, black body cavity is called the black body radiations. It's called the black body radiation. It's known as the black body. So gas of photon means that the radiation. So they radiate the waves, and we can think of a gas of photons. So this is known as the black body radiations. So now we do some problems on this black body radiations. So let's consider. Okay, so far any questions? Okay. So let's consider Earth and Sun behaves as a perfectly black body. So the question one is that let's consider Earth and sun behave as a black bodies. Behaves as a black bodies. And the temperature of the earth's surface is maintained by the radiation from the sun. The temperature from the temperature of the earth's surface, the temperature of the earth's surface is maintained by the radiation from the sun. Maintained by the radiation from the sun. So then, what is the ratio of the earth temperature and the sun temperature? Calculate is T earth versus T sun. Calculate this. So how to calculate? So what is the power sun emit? So, so earth and sun are both the black bodies, and the temperature of the earth's surface is maintained by the radiation from the sun. So what is the power that emits sun? So the power emitted from the sun power emitted from the sun can you tell me what is the power emitted from the sun? Let's say P sun, the power emitted from the sun. So we denoted that S is a sun and earth is P. So power emitted from the sun PS. What we learned so far? This is what is the power? The power is that sigma T to the power 4. That is the Stephen Boltzmann. And this remember this power incident and emissions are equal. So power emitted or incident per unit area. So here we enter the power emitted from the sun. That means the sigma T sun is to the power 4 times the area. Okay. So what is the area? This 4 pi r sun square. Right? So they emitted throughout the surface. So this is 4 pi r square. This is surface area, right? And this the RS is the radius of the sun. This is the this power is known as the luminosity. So this power known as the luminosity. So this power known as its luminosity. Known as its luminosity. So what is the unit? The unit is the watt. Watt is the unit. So sometimes in the problems specify the luminosity rather than the power. It means that the power is the surface area multiplied by surface. That's called the luminosity. So now at a distance d from the sun, this power is uniformly distributed. So Earth to the sun distance is the d. So d is the distance between Earth and sun. So d is the distance between Earth and sun. So this luminosity is uniformly distributed over a sphere with a surface area is 4 pi d square. So let's say this is your sun and this is source. So this is spherical power emitted, and you will say that at some distance d. So again this is uniformly distributed over this surface, right? This is a distance d. So this is a sun. So this is a sun surface. This is a sun surface, and this is a earth surface at a distance d. Let's make it different color. So at a distance d, earth surface. So this whatever emitted from this sun surface, okay, this is uniformly distributed over the earth surface 4 by d square at a distance d. This sphere. So earth only catch this power over the projected of this earth surface. Okay. So that means that the power incident on the earth, power incident on the earth is this luminosity L times. So this luminosity distributed uh, uniformly at a radius spherical surface, right? But earth only catch those power which is projected on this surface, right? So that means this L times pi r square earth, the radius of the earth, by 4 pi d square. Because the only these portions, let's say the earth, so the radius, how to draw this thing? Yeah. So let's say this is your earth surface. So only, so this is a, let's say, earth surface, and this the earth radius is re, right? So only these portions, and this is the pi r square. This is, so only this catch, only these portions catch this radius, not the whole earth surface catch this radius. So the portions, that is the pi r square, peaks. So this point is clear or not? So only these portions catch this radius, not the whole surface catch this radius. Okay, so this point is clear. or not? So if it's not clear, then please write your voice, then I can discuss again. Okay, so think about it, and so this is a power incident on the Earth. Now, what is the power emitted from the Earth? So again, the Earth is a perfect black body. So power emitted from the Earth, power emitted from the Earth is equals to again the 4 by r square times sigma T e to the power 4. Right? So both Earth and Sun have a uniform temperature. So this power incident and power emissions are equals. So once we equate these two things, we get the so equate the power on the Earth's surface, equate the power Earth surface so we get that 4 pi r e square times sigma t equal 4 equal to the luminosity. We know that the luminosity is sigma t is to the power 4 times 4 pi r e square times pi r e square by 4 pi e square. So the sigma is the Stephan Boltzmann constant. It's a universal constant. So this is same for the both black bodies. When you are considering the both of the perfect black bodies, both of the black bodies, so sigma is the same. So you can cancel this thing. And 4 pi is a constant, so you can also cancel the 4 pi. This pi and this pi cancel. So at the end, you get this T earth, T e over T sun, root of R sun, square root of R s by so now the d is the distance between the earth and sun. Let's do it on specific examples. So putting the number, let's say r sun, r is, let's say given r is 7 times 10 to the power 8 meter, right? Earth, radius of the sun. And what about the d distance between earth and sun? It's 1.5 times 10 to the power 11 meter. Okay? And what about the d sun? Let's say 5800 Kelvin. So you can easily calculate once this data is given. You can calculate T earth. What is the earth temperature? So you can easily calculate the earth temperatures. 5800 7 times. So about 280 Kelvin. earth temperature is around 300 kelvins. So it's not bad. Even with these assumptions, the totally assumptions, both are the perfect black bodies. But the result is it's still reliable. Okay. It's not bad. So the earth temperature is around 300 kelvins. So let's do one more problem, and then we can discuss what is the possible cases. Okay. Okay. So far, any questions or from this problem, if you have faced any questions? Okay. Let's do one another problem. Is that so let's consider a spherical black body. Let's see, let's consider a spherical black body of radius r, absolute temperature T. So spherical. So I got a black body as a baby. So spherical black body of radius r, okay, and absolute temperature. So when we write the temperature, the absolute temperature. So temperature is T. It is by surrounded surrounded by the spherical cell, another cell. The spherical cell. Okay, so thin spherical and concentric cell. The center is safe. Concentric cell of radius capital R. So one is the smaller, another is capital R, which is greater than smaller. That means the surrounded, right? Okay. Uh, yes, and black on both sides. So this spherical, the thin spherical cell black on both sides. Black on side. So calculate the rate of the cooling of the body reduced by this radiation shield. So question is that calculate the rate. Okay, so calculate the rate of the cooling of the body reduced by this radiation shield. Reduced by this radiation shield. Radiation shield. So consider that the space between the sphere evacuated and there are no thermal conduction losses. So written is that consider the space between the cell, sorry, between the sphere or cell, whatever you call it, sphere evacuated with no thermal conduction losses. Thermal conduction losses. Ah, so what is the question and how to solve? So consider a black body of radius r and the surrounding temperature is, let's say, T naught. So let's say the surrounding temperature is T naught. So which surrounding is the first black body? Is of radius r. So the rate of energy loss of the black body before being surrounded by a spherical cell. So let's first consider only one black body of radius r. So the spherical black body of radius r, and there is no other concentric cell. So only just this black body is there. Okay, and the surrounding temperature of this black body, is, let's say, T naught. Okay, so the rate of energy loss of the black body, then Q, the rate of energy loss, that means the flux, okay, emitted, that is the power emitted this of the black body. So the rate of energy loss is Q equals to 4 pi times r square times sigma the rate, right? So surrounding temperature T naught and your black body temperature as T, right? So this T to the power 4 minus T naught to the power 4. This is the rate, right? Okay, so black body temperature is high. Okay, so T is greater than T naught. That's why they are emitted. Okay, and the rate of energy loss is 4 pi times r square, the area. Okay, surface area times sigma to the power 4. And this is the rate, that means the difference this. So now the energy loss per unit time by the black body after surrounded by this cell. Now we surrounded by concentric cell of radius capital R. Now we surrounded this by another spherical cell of radius capital R, which is greater than equal to small r according to the questions. And the power emitted then or the energy loss per unit area. So write the energy loss per unit area. Energy loss per unit area, sorry, unit time. Energy loss per unit time. What? So energy loss per unit time Q prime is 4 by r square times, let's say, T to the power 4 minus T1 to the power 4. Right? So T1 is the temperature of the this spherical cell. Okay. So this is a big spherical cell. that temperature, let's say T1. So that is a temperature, let's say T1. So then the energy loss, then the energy loss per unit area, per unit time is 4 pi r square times, now T2 not T naught is T1. Okay. Yes, T naught is the surrounding temperatures. So what is the energy loss by the cell? So this is the energy loss per unit area by the SSB, spherical black body, SBB, by the spherical black body. Next, the energy loss by the spherical cell. So cell is the outside. This is surrounded by thin spherical cell. Okay, so outside spherical black body. Okay. So this is a cell. So next, the energy loss per unit time, per unit time by the cell, Okay. Let's say Q double prime. So it's 4 pi times capital R square times sigma times T1 to the power 4. Now the surrounding temperature is T0. So T0 to the power. So spherical black body T at temperature 2, the spherical cell, okay, T1 at temperature, so T2 T1, and then this T1 to T0 surrounding temperature. Initially, so this is the initial, there is a no spherical cell. So that's why we are going for T to T0. But now we surrounded by the spherical cell. So that means they radiate from this energy loss, this T to T1, and by the spherical cell, the energy loss by T1 to T0. Because T0 is the surrounding. So now, since that this spherical cell, okay, the emission and absorptions are equal. So that means the Q prime equals to Q double prime. So this Q prime is energy loss per unit time by the spherical black body. Energy loss. So this energy loss compensated by the spherical cell, and the spherical cell energy loss this. So even the temperature is the same T1, so that's why this Q prime equals to Q double prime on the spherical cell. So we obtain this T1 to the power 4. Just equate these two things. We get this R square times T to the power 4 plus capital R square times T0 to the power 4 by R square plus small r square. So hence Q prime by Q, so which is get R square by R square plus R square. So that means the energy loss after the surrounded by the cell and before the surrounded by the cell. So this Q is that the before. So before the surrounding by this cell, this is the energy loss Q, and after the surrounded by this cell, this is the energy loss Q prime by the same body, spherical black. So now we take a ratio of this Q prime by Q. This is that R square by R square. This is that the how much effect, the calculate the rate of the cooling of the body reduced by this radiation shield. So once we add this spherical cell outside, what the reduced, that's is calculated. This is the ratio. So cooling means that the loss energy. So that's why the cooling. So and the rate of the cooling of the body, how much reduced by this radiation shield. So we take the refill. So after the shield and before shield. The second, let's say consider on let's do one another simple examples, and then we discuss some black body thermodynamics. Okay, so let's consider the solar constant. Okay, so what is the solar constant? Solar constant is that the radiation flux at the surface of the earth. The radiation flux at the surface of the earth. Surface of the earth. And let's say given the solar constant. So given the solar constant equals to 0.1 watt per centimeter square. So this is the given the solar constant. And find the temperature of the sun, assuming that it's a perfect black body. So once we given the solar constant and we calculate the find the same temperature of the sun. The temperature of the sun. Assuming that sun it is a black body as a black body. Assuming that the so it is a black body. Assuming that it is a black body. Black body. Okay. So how to calculate? So what is the power per unit area? Okay, but once we know that the sigma T to the power 4, right? Because we calculate the temperature, so it's better to calculate the relate to the temperature directly. So because with the sigma is a universal constant, so we know the sigma. So if we know that the sigma, so it's the 5.7 into 10 to the power 8 watt per meter square. Okay, so this sigma constant is a universal constant. So how to remember this? This is a 578. So 5. This is actually the 567. 5.67. Or you can write 567 and 10 to the minus 8. That is a 5678. In this way, you can remember that the values of this function. Okay, so then if you calculate the power, so now solar constant, the radiation flux at the surface of the earth. So that means this sigma T to the power 4 times R sun square divided by HD square, and that is that the 0.1. So radiation flux, so this is the power per unit area. That's the radiation flux per unit area. Unit area. So if we multiply it with the area for the sun surface as a square, and the earth to sun distance is the d. So d is the distance between the earth and sun, distance between earth and sun, and this is that the radiation flux at the surface of the earth, right? So 4 pi r square by 4 pi d square, so times 4 pi r square by 4 pi d square. So this is the fraction of this the surface of the earth, right? And this is equals to 0.1. This one is clear or not? So sigma t to the power 4 is emitted from the sun per unit area. So now multiplied with the sun surface area, so 4 pi r square. So that means that the total power emitted from the sun and how much fractions reach to the at the earth surface. So it's divided by 4 pi d square. So they are uniformly distributed. So it's divided by the 4 pi d square. So that is actually 0. So given the solar constants. So that is the solar constant, the radiation flux at the surface of the earth. Okay. So this is a solar constant. So this is equals to 0.1. Right. So now once you know this RS, so what is the RS? Just to write down in the previous case, that is 7 times 7 times 10 to the power 8 meter. So the RS is 7 times 10 to the power 8 meter. And what about D? So you know this, the values of D. I just write it here. Yeah, so 1.5 into 10 to the power 11 meter. So 1.5 into 10 to the power 11 meter. So if we put, we can calculate T, right? Temperature of the sun. So temperature of the sun. And you have to calculate it, and you can calculate it. 6 times 10 to the power 3 Kelvin. Right? So now you know that the sun temperature is 5800 Kelvin, right? So that's a 5.8 into 10 to the power 3. So we get here the 6 into 10 to the power 3. It's not bad. Because we assume that the sun is a perfect black body. So we are immediate measurements. But the result is good. It's not bad. So in this way, we estimate the temperature, the sun temperature, right? So suppose you given the solar constant is not 0.1, let's say 0.2. So this is a bad. It's a bad input because they gives the sun temperatures it's too much deviate from the exact value. So not exact, but it's appropriate values. So once the given the sun temperature, you can keep a constant the solar constants, or once the given the solar constant, you can calculate in this way the sun temperature. So just using this the Stefan Boltzmann law and this kind of things, you can solve the problems. The other problems are just the things that once we so if the temperature of a black body is increased, let's say the big problems that if the temperature of a black body, let's say, increased to black body temperature, let's say increase to T to 1.4140, let's say root 2. Okay. So by what factor of the total emitted power per unit area increased? So what factor is the total emitted power per unit area increased? Emitted power per unit area. So we just apply this the formula, that is the power P per unit area is the sigma T2 by P. So now we have divided by this P1 by P2. The sigma is the same. So it's just a T1 by T2 by 4. So we get this. Just put into the formula, we get that R. 2 times R. So if so this is this way you can calculate. Because T2 is root 2 times T1. Hello. If you have any questions, then otherwise please unmute mute yourselves. So root 2 T1. So once you put these things, hello. If you have any questions, otherwise please. Okay. So then we can in this we can easily calculate. Similarly, yeah. Okay. So today I think all this time is over. Okay. So I can continue to the this problem solving to the next series. I mean the 21st one April, and we will solve overall the problems from the first class to uh, so far, so till now. So please be there and so if you are prepared for the exams and clear your doubts, these kind of things, okay, and or if you have any questions so far, so then you can ask. Okay. So, so the last schedule is the 21st on April, sir. And it's only dedicated to the those are only appeared for the exams. Okay, and I will do most like the problems for this. So there is no discussion. But you can, if you want, then we can discuss something. But we will mostly solve the some problems. I will choose from each of these topics from the week 1 to week 12 and solve one or two problems from each of these. So those students are appear from the exams. I request you to please be there and the last series. And if you have any questions or any doubts, you can also clear. It might be helpful for your exams. Okay, so we will see in the next series. I will stop. Thank you.